The common theme is analysis of longitudinal data. So there is this common theme that holds the talk together. But I will focus mostly on ideas of modeling and see how you can borrow ideas from one type of analysis and use it successfully for another kind of analysis. So I'm going to start by talking about modeling ideas in multi-level factor analysis, although we will pay fairly little attention to multi-level factor per se. And I'm going to use that as a basis for moving into structural equation modeling of a very familiar kind, as you will see. And then I'm going to take ideas from that first bullet into the second bullet and talk about latent transition analysis and new extensions of that. Then I'll move into multi-level time series analysis of intensive longitudinal data, and we will see how these ideas play out in that context. And finally, I'm going to end with Bayesian analysis of count nominal and binary loaded outcomes, which is a new feature that we just developed. And that also relates to, in the example I'm going to show, it relates to longitudinal analysis, coming back to the classic topic of panel data analysis and cross-lag panel data analysis. And as I said, this draws on material in several present and future web talks, which go through it at a slower pace and where you also see how to carry this out in software in Mplus. So assuming you're all still there, I'm talking to this empty room. So here is multi-level factor analysis, where you have a set of observed variables, y, for individual I in cluster J. And you write it, you decompose the observed variable into two latent variable parts, a between part and a within part. Between part varies across the clusters. Both of these are latent variables, just like random effects ANOVA. But we're going to put a structure on the between part and a structure on the within part, writing it as a factor analysis model, where we have the slopes, which are called factor loadings on the factors, on the between level, and the residuals, and then the analogous arrays for the within part. So the covariance structure then for the observed vector is sum of the between covariance matrix and the within covariance matrix. And each of those has a factor analysis structure, the famous lambda psi lambda prime plus theta expression using the notation of Carl Jursgård. And it's interesting to think about this for a couple of seconds, that in education, there has been a long-standing interest in analysis of cluster samples, because we observe students within classrooms and schools. And I think maybe in education, it started with Lee Cronbach's work, Cronbach of the Cronbach alpha fame. He had an unpublished paper which seems to have spurred a lot of research in future years by his students and himself. He talked about, for instance, slopes as outcomes, beginning of multi-level analysis, where you have random slopes in regression analysis, but he was also interested in factor analysis. And a fellow Swede, Kjell Härnqvist, came and visited him at Stanford and got inspired by that and took it home and applied the methodology to school data that he had in Sweden. And in those days, it was just trying to match a covariance, fit a covariance matrix within on a pool within covariance sample covariance matrix, you know, cluster mean centered, group mean centered, and then looking at the covariance matrix for the cluster means. All of that got distorted because it has within cluster variation in it as well. But Harvey Goldstein of Emil Wynne fame and Rod McDonald pushed this and formulated a proper maximum likelihood framework for how to do this. There's a whole bunch of other references, including some of mine, of course, but I couldn't fit them on the page. So if you take a look at this, same model in the case of where you have one factor on each level. You have then just one single factor B and single factor W, and you have the loadings, which is then a vector instead of a matrix. If you look at that long enough, it will confess to you that it's really a two-level model. You could write it as on level 1, y is a function of nu, that's the intercept, plus the within structure, where nu sub j varies across the clusters, and therefore is a level 2 variable, which has this mean and this covariance. This gives a covariance structure of the factor analytic kind. So if you insert level 2 nu j up here, of course you get this equation exactly. So that's just a different way of looking at it. So the two key aspects here is that two-level factor analysis can be viewed as a random intercept model where the intercepts have a factor structure. They don't need to have a factor structure, and sometimes we don't, but that was the typical application. Now, because the random intercepts appear for the factor indicators up here, measurement non-invariance is allowed. You know, we have invariance across clusters with respect to the lambda sub w, but we don't have invariance with respect to the intercepts. So built into this model is something that we didn't pay attention to before. I'm sorry, is that a question? Okay. So we allow for a certain degree of measurement non-invariance here across clusters, but it's a disciplined non-invariance that we model, and the clusters have this common set of parameters. This measurement non-invariance perspective, I discussed that more in detail and gave a lot of references to other people's work also in Mplus Web Talk number 1, which is on the Mplus website. But it's a theme that we're going to come back to through this talk. So in the model diagram then, and I'm going to talk in terms of formulas, but also in terms of model diagrams, because some people prefer formulas, some people prefer diagrams like the one at the bottom here. I want to emphasize the diagram format because it gives a visual connection between different model types. If you see it written out in a picture, you can more easily see how it hangs together, how it relates to other model frameworks. So we're going to have random intercept represented as a factor, a latent variable with the unit slope. You know, if you go back here, it is certainly having a unit slope here. It influences y with slope 1 fixed. So we have these, on the between level, we have the between level factor, and we have these random intercepts, which are continuous latent variable on between. And on within, we have the observed variables, and we have the within factor structure. And we also mark where we have the random effects by these filled dots for the observed variables. Those filled dots become open circles, random intercepts. And it's this part of the model is of computational interest when you have categorical or other non-normal outcomes, because it relates to maximum likelihood estimations, numerical integration issues. So if these were dichotomous variables, you would, on the between level, incur 6 dimensions of integration, which is very heavy for maximum likelihood. If you reduce the dimension of these 6 to 1 factor and drop the residuals here, then you have 1 dimension. So 6 dimensions go down to 1 dimension. And that becomes important. And it's not a bad approximation, because on the between level, correlations are higher than on the within level. We have these ecological correlation issues, and the residuals are often quite small. So it's not a bad approximation. So the example here is students within classrooms, achievement testing. So it could be, these first 3 items could be, or tests could be math tests. These could be reading tests. You have 2 factors for students. But on the school level, this could be just an excellence factor, quality of school. And therefore, you get different number of factors and different interpretation of the factors. On a more granular level, this could be math items for algebra or algebra topics, and this could be math items relating to geometry topics, two different factors. And then the variation could be across classrooms, where classrooms may differ with respect to how much time they give to math teaching, such as the issue of tracking in math classes in the US. Now let's go deeper into the multi-level factor analysis and simplify it to just 3 variables, 3 random intercepts, and 1 between-level factor. Now we ignore the fact that with 3 random intercepts, 1 factor, this is just an identified model. It's the same thing as letting these 3 random intercepts be freely correlated, but we'll keep it this way. So we think we're now in the cross-sectional setting, students within schools, but the case of time points nested within individuals is also multi-level. So why not apply this thinking to longitudinal data? Time within people. So here is what multi-level factor modeling can teach us about single-level modeling. We're now going to look at a longitudinal model for t equals 2 time points, time 1, time 2. So let's look at this for a while because there's a lot of stuff to note. So we started with this model up at the top here, top left, which is the cross-sectional setting. And now we're going to talk about 2 members of each classroom, so to speak. In this case, the members are the 2 time points, time point 1, time point 2. But for both time points, you have the same influence of the random intercepts here. They all have unit loadings here, unit loadings going there. So all of these are equal. They're actually fixed to 1 here. And also, you have the same factor loadings here as over here on the right. And even invariance with respect to the residual variances on the within level. So this is taking the multi-level factor model thinking into a longitudinal framework, longitudinal setting. And you can, this is then modeling in a, not in a multi-level fashion. What you're looking at here is a single level model in wide format. So in the multi-level setting, you have 3 variables, 3 columns in your data. But in the single level wide format, you have 6 variables in your data, 6 columns. Now, I'm not the first one to think about this. Actually, Hammaker and others had an MBR, multivariate behavior research article on this, where she talks about the so-called CUTS model, common and unique trait state variables or factors, based on multi-level factor analysis. So we're going to see here, this is the first example of making a connection between random intercepts and latent traits of psychology. So this is multi-level based longitudinal factor analysis that allows differences between person trait-like factor structure and within person state-like factor structure. And she argues, just like Cattell, that factors from cross-sectional factor analysis may be confounded by both between and within person covariance, referring to Cattell's early work. And you get an uninterpretable blend of results, to quote Raudenbusch and Brag's multi-level book from 2002. It relates to, if you look at the bottom bullet, it relates to a lot of latent state trait or latent trait state work. Herb Marsh, 1994, Ide, and let's see, Geiser has done a lot of work on this, Christian Geiser at Utah, and he just came out with a book on it, on longitudinal structural equation modeling from a latent state trait perspective. Now, what I want to do is take this longitudinal factor analysis based on multi-level thinking a little bit further by having a influence regression of the within level factor on the on the at time 2 on the one at time 1. So that's how we extend this with this auto regression. You can think about this, if you go back to the cross-sectional model now, cross-sectional thinking, it would be students within school influence each other. So on the left you have student 1, on the right you have student 2, like leaders and followers type of thinking. Now this multi-level based longitudinal model is quite different from naive longitudinal factor modeling, which uses only the bottom part. It doesn't use the part up here, typically, unless you're used to latent trait state thinking. So that idea is quite powerful, even for very classic structural equation models, as we will see. So 46 years ago, I was a student in the statistics program, graduate program in Uppsala, under Joris Good's leadership. Excuse me. And I decided I wanted to go and visit the US to get ideas for a dissertation. So here we have the social science building of Madison, Wisconsin, with its Korean bell tower here. It looks like the Leaning Tower of Pisa here, where you have the economics and sociology departments in there. So I visited with the econometrician Art Goldberger and the sociologist Bob Hauser, and came up with an idea for my dissertation because thankfully the sociologist Odestad Duncan had left a written out unsolved problem and left it on the desk of Art Goldberger. And Art showed it to me, and that became the first paper of my dissertation, structural equation modeling with dichotomous outcomes. That ended up in JASA, but much more well-known paper is the one I wrote together with Blair Wheaton, a sociology grad student who wanted to use Lisrel, which I had just been educated on at Uppsala. And we wrote this paper, 1977 paper in sociological methodology. Here is the model, the classic Wheaton et al. Structural equation model. It's classic because it ended up as a toy example in many users' guides by many software pieces, including Lisrel, typically using only the first time point, first 2 time points, I should say, whereas in the this sociological methodology chapter, we work with 3 time points. So time point 1, 2, and 3. So just look at this for a second here. We have the 2 measures at each time point, anomia and powerlessness, measuring some sort of alienation factor. We repeat those measures at other time points. And we want to look at the stability of alienation across time. This is 1966, 1967, and then a longer jump to 1971. And you have then, you want to take care of the measurement error that sits up here when you assess the stability here. And you want to relate it to socioeconomic status, the Duncan SEI index, and education down here. And then I had just learned about correlating residuals in Uppsala, so I wanted him to correlate the same item across time because of other influences common to that item. And the model ended up looking like this. It's not a great model. You should never work with only 2 indicators per factor because you have no chance of testing the quality of this measurement model at each time point. And there are many other questionable parts of it. Maybe SCS should be a formative factor where these variables influence it instead of being influenced by it. But let's put that aside. The important thing is this is a fairly frequently occurring type of model situation. But from what we have learned now in the previous slides, we really should instead look at this model this way. This is a random intercept version of this model. What we have here is a model which still works in a single level wide format, but we're drawing it in a way that suggests there is a between part and a within part. The between part refers to variation across individuals, and the within part refers to variation across time. So we have then the two random intercepts, A and P, for the two types of items, which have unit effects on all of those items. And they are affected by, influenced by the between level factor SES. And what you have then left here is within person dynamics over time. You don't have any connection between these variables and the within level variables. So you split it up like this. So that's an interesting redrawal of that model that I haven't seen before. Here, so again, we have the thumbnail sketch of it, still a single level wide model, two random intercepts representing between level variation, instead of all of those correlated residuals. And note that this, if you go back to the correlated residuals that we have here, you could have a autoregressive residual structure as well. But what we're doing when we introduce a random intercepts, it is not a correlation across time for the residuals that gets smaller and smaller across time because of the time distance. It's a constant correlation, constant contribution across time, which is the idea of random intercepts and is the idea of latent stable traits. And SES is between level variable, and the relationship between factors over time represent within person dynamics. So let's see, classic versus new. How do they compete in a sample of 932 individuals? So you have the number of parameters here, 31 for the classic, and the new has only 25 parameters. But lo and behold, the log likelihood is better. This number here, 19425, is a higher likelihood than 19455. So with fewer parameters, we get a better likelihood. And therefore, of course, we get a much better BIC. Chi-square was 90 with 13 degrees of freedom, p-value of total 0. Chi-square now lower despite having more degrees of freedom. And we actually inch up to 4%. Not quite the 5% level, but getting close there. And a much better root mean square error approximation and a better CFI. And interestingly enough, findings for this new random intercept model is that on level 2, SES has a significant negative effect on the random intercepts. The more higher SES value you have, the less alienated you tend to be in a general rough sense. So that makes sense. And SES explains this measurement in non-invariance that the random intercept represent. Explains this variation across people. And on level 1, the within level, you do find positive effect of F1 and F2 from 966 to 67, but there is no significant effect on F2 and F3. F2's effect on F3 is essentially 0 and insignificant. And there's a longer time distance there as well, which is totally different from the findings of the original model. And you can certainly relax this new model in several ways because we have across time equalities of everything, basically. And for instance, you could relax the cross time equalities of the residual variances. Very restricted model, having much fewer parameters, but it's the right type of model, it seems like. So I tried that out on a couple of other longitudinal multiple indicator data sets and find the same results, that the new thinking works well. All right, first bullet is done. Let's now take this knowledge into the realm of latent transition analysis, which is also a longitudinal analysis matter. So statisticians talk about hidden Markov modeling, and they tend to work with situations where you have a single variable at each time point and many time points. Whereas in psychology, you typically work with multiple indicators, in this case 2 per time point, and rather short time series, in this case only 3 time points. So now we switch from Y to U to denote the fact that the variables, the observed variables, are typically categorical, very often binary. And C, the factor, is now also categorical, so it's a categorical latent variable, a latent class variable. That is, you are now in the finite mixture context. Now the LTA features, and in Web Talk number 1, I give a lot of references to work by, for instance, Linda Collins and many others. You have a measurement part of the model, which is, like in factor analysis, the relationship between the latent variable, which here is categorical, and the observed variable. So it's a probability of the use, the binary use, given the class that you're in. And that's a latent class analysis model for each time point, each of these 3 time points. Typically, you hold a measurement invariance across time to support the fact that you're talking about the same latent class variable across time. Now, the second component of the model is the initial status probabilities, the probabilities of the classes where you start the series. And then you have the transition probabilities, C2 given C1, C3 given C2. Typically, you don't include the lag 2, but that can certainly be done. And extensions of that is to work with covariates. Covariates that influence the latent class probabilities and the transitions across time. You may also do multiple group analysis, where you look at measurement invariance for different groups. So seeing that these conditional probabilities in the measurement model are the same across different kinds of groups, male, female, for instance. And there's also an interest in so-called mover-stayer modeling, where stayers are those that stay in the same class with probability 1 and move to other classes with probability 0. So you have another layer of a latent class, the movers and the stayers, 2 categories, latent class variable, extra latent class variable, and that's quite possible to model as well. So what's missing in these models now that we're looking at? Well, given where we come from, obviously, these are repeated measures model. It's a multi-level setting in a sense. If we do it as 2-level long instead of single-level wide as we draw it here. I mean, think about the single-level wide in a 2-level long format. You immediately want to use random intercepts, perhaps random slopes too, but at least, very least, random intercepts. So that's a glaring omission from that perspective. From a statistical perspective, then, you would think of multi-level modeling with level 1 time, level 2 subject, and therefore you want to have random effects, especially random intercepts, as I just said. And from a substantive perspective, that relates to trait theory in psychology, the random intercepts, which is another reason that folks correlate over time, not only through the latent class variables. Latent traits are between subject differences that are stable over time, which is exactly the definition of random intercepts. When you get to the multiple indicators per time point perspective, that is top right, you get into psychometrics about measurement non-invariance, and there's a lot of attempts at taking care of multiple indicators in the multi-level setting. I just touched on multi-level factor analysis, but it's also a whole literature on multi-level latent class analysis that you can draw on. Now, hidden Markov modeling with random intercept does exist in the statistical literature. So you have this JASA article by Altman, and this woman apparently did a dissertation on this, mixed hidden Markov models. So she adds a random intercept up here. So it has, unit slopes here, fixed for 3 time points. There's only one random intercept because it's only one variable per time point. So it looks like just a factor influencing them all. And she applied that to multiple sclerosis patients. Symptoms worsen and improve in alternating periods of relapse and remission. The outcome is number of lesions in the brain is actually a count variable to make it even more difficult. and she looks at t equals 24. So the typical hidden Markov setting, 2 latent classes, relapse versus remission. But that doesn't seem to have been picked up in the psychology-oriented applications. And I don't know how frequently it's used in statistics either. The hidden Markov model on the left is, after all, quite much more easily estimated by ML, by this backward-forward or forward-backward bound-Welsh algorithm. The random intercept model on the right loses its simplicity. The U's are no longer independent conditional on the C's. On the model on the left, the U's are independent when you condition on all of these 3 latent variables. But here, the variables correlate not only through C, but also because of U, which means that ML estimation is going to need numerical integration with much heavier computations. And here's a book on that that describes these kinds of models. But this is for the single indicator case. And like I said, it doesn't seem to have been picked up in the multiple indicator LTA case. We did that, my colleague Tiamat Sparaho and I, and formulated a model like this in a paper that's forthcoming in Psych Methods. So what we did was to introduce a random intercept factor here, and now we notice 2 things here. Even though we have 2 indicators per time point, we have only 1 factor here. We could have had 2 intercepts here, 1 for each of the indicators that influences all time points equally and estimate their variances. But that would have meant 2 dimensions of numerical integration, and with 5 or 10, there would have been 5 or 10 dimensions of integration. So what we do here is have 1 factor that influences these 2 items differently with different loadings, lambda 1, lambda 2. They're equal across time, but they're different within time, so different for the 2 indicators. So this relates to that simplification from a numerical analysis perspective that I talked about before. Actually, I went through a lot of data and analyzed it both ways as much as I could in terms of the dimensions of integration. And this model, actually, in terms of VIC, almost always wins because of its simplicity. So we have a whole page on this here on the Mplus website with setups, scripts for all of these, and data set that you can practice on. And I've just written a web talk that describes how to do LTA and random intercept LTA in Mplus in utter detail. Probably going to be a 3-hour talk, but broken up in segments. So that's what it looks like. And to make that work in practice, Tiamat and I had to improve the software. Because this random intercept LTA can be time consuming due to this numerical integration. Even though it's only unidimensional integration, you need many random starts to find the global maximum, and that can take time. So we came up with a version 8.4, now we're at 8.5. 8.4 released last year with significant speed improvements using a new 3-stage random start search. And here, a 20 hours computation in Mplus 8.3 can be done in 8.4 in less than 15 minutes by utilizing advantages of the 3-stage estimation, the Baum-Welch algorithm, as well as updated hardware, recommending the i9 Intel CPU. The most interesting finding is that regular LTA fits typically worse than RI-LTA most of the time. So here you have 4 data sets from the LTA literature. Life satisfaction, which is from a applied latent class analysis book by Hagenars and McCutcheon, as 1 indicator per time per 5 time points. And you see in our parameters, RI-LTA adds 1 parameter in the single indicator case. And you see how VIC goes down. This is a better VIC. than for regular LTA. And here's Michael Ide's mood data, 2 indicators, regular LTA big 4150 and a better big for RI-LTA. Here is dating and sexual risk behavior. It's an article by Stephanie Lance and Linda Collins. 3 time points, and it is 3 indicators per time point. And here too, 32,796 goes down to 32,502. Quite a big improvement. But we're going to take a closer look at one data set, reading proficiency, which is not in the paper forthcoming in psychological methods, but I treated it in detail both in Web Talk 1 and Web Talk 2. So here you have 4 time points, and you have 5 indicators per time point, 5 more parameters. Likely gets much better, but you have more parameters, so that's natural. But so you have to have the arbiter here in big, 4985 instead of 43,873. Quite a large drop. So let's take a look at this data in more detail. So the data come from the early childhood longitudinal study, equals SK, kindergarten, I guess. But 3,574, fairly large sample, which we like to have for making transition analysis. So 4 time points, fall and spring of kindergarten, fall and spring of grade 1. We have 5 binary items representing mastery of the basic reading skills of letter recognition, beginning sounds, ending letter sounds, sight words, you know, when you look at a word without spelling it out, you see what it is, words in context, which is a more advanced topic. And the article found 3 latent classes corresponding to 3 stages of learning: low alphabet knowledge, early word reading, early reading comprehension. Now here we analyze those data by regular LTA at the top and random intercept LTA at the bottom. So first we have to get used to what's in the columns and the rows here. So the columns are the 4 different time points, and the rows are the class probabilities. So this is the lowest reading skill class, middle, and the highest. So in the fall kindergarten, these probabilities add up to 1. So in fall kindergarten, most kids are at the lowest point here, 69%. And then they march over to become more common in reading level 2 in spring, in fall of first, and then ending up with fairly high probability of being in the highest reading ability class in the spring of first grade. Now for RI-LTA, class probability is much higher for fall of kindergarten, so giving a much more negative view. That's quite a distinct difference here. And at the end, a difference as well, saying that regular LTA underestimates class percentage in class 1 in the beginning and underestimates the class percentage of class 3 at the end. And if you look at the data for the first time point, for the 5 latent class indicators, it clearly shows that the regular LTA model is misfitting here compared to this. So you would draw quite different conclusions here depending on which model you use, which is the point of the paper. Now, if you look at the transition probabilities, previous slide was just class probabilities. They are a function of the initial status probability and the transition probabilities. So transition probability, I'm just looking at 2 transitions now. There are 3 altogether, of course. Fall K to spring K for the 3 classes, low, medium, high. low, medium, high, for regular LTA and for RI-LTA. So you have the diagonal is bolded here, so we find ourselves, orient ourselves more easily. So you have a probability here of staying in the same class, which is higher than moving on to the next high level. So this is, sorry, did I say that backwards? So the probability is higher that you move on than stay in the same class. You see that also for RI-LTA, but the probability of staying in the same low class is lower. The probability of moving on is higher than for regular LTA. So again, a different substantive conclusion there. Now, RI-LTA can also be extended to covariates. Here we have a covariate X. And if you look at this picture now, it looks a little bit similar to another picture we looked at before. Namely the Wheaton et al. Model rewritten as a random intercept model inspired by multi-level factor analysis. So you have a random intercept factor here, same as before, but you add the X, and now we have X is a variable that varies across people, but not across time. So a time invariant covariate influences the random intercept factor here. What's new in this model, though, is that you can actually have these direct effects as well. This is identified, which it wasn't in the continuous case with continuous variables, continuous factors. So the linear covariance matrix setting of Wheaton's model does not allow the identification of these direct effects. Where here we are in a very nonlinear situation, you know, with nominal variables here, binary variables there, not linear relationships anymore, and it's possible. But the more interesting point is that this random intercept factor can be seen as a latent trait. It is the constant time invariant influence on the outcomes over time, making the transitions be related to within person development across time. All right, we're doing well in time. So now, multi-level time series analysis is a topic that we spend several years on in the Mplus group, trying to develop that. You know, most time series analysis is for what we would call n equals 1. That is watching and analyzing the smog in Los Angeles, that is analyzing LA only, not other cities. It's a big literature on that. But what we focus on is the multi-level case, where you have several individuals in our case that have parameters in common. And you can formulate it as a multi-level model where aspects of the time series model parameters are random. So random effects that show variation on level 2, that is variation across individuals. So we're in the same setting as in the other cases. It's just that we look at a somewhat different situation. So once again, repeating the random intercept LTA model here, written now, and you have to be able to go back and forth between single level wide, 2 level long. This is clearly written as a single level wide format model, but it has a random intercept there, so we know its connection to the multi-level or 2 level long situation. One thing that you do in the wide format is you get relationships across time here. But in the regular multi-level factor analysis model, you don't have those relationships. You don't have students influencing each other in the standard multi-level factor analysis model. You could, but you don't in a standard one. So how do you analyze relations between variables at different time points using two-level modeling? And why would you want to switch to two-level modeling in the first place? Well, it's because, of course, sometimes we have so many time points that going in the wide format gives us too many columns in the data, too many variables to analyze that it breaks down numerical analysis wise. So for that situation, you want to work with a multi-level setting, but you don't want to give up on these relationships across time. Well, multi-level time series analysis offers this possibility of having long time series while at the same time be able to have relationships across time. And you can have a lot of random effects, random slopes, random variances, random autoregressive coefficient, random transition probabilities in the LTA context. Although that kind of flexibility, of course, going beyond random intercept, requires many time points. But you have that when you have these so-called intensive longitudinal data as you get in ecological momentary assessments or experience sampling methodologies or in daily diaries. And we're going to see examples of that. So if we look at this slide then and take our time with it because it's pretty intense, I'm now going to try to bring you over into what we call dynamic structural equation modeling, DSEM. So if we start on the left in the single level wide format, we have the picture exactly that we drew before. And now we're going to move that to the two-level long format. So on the within level then, we're going to have two observed variables, so two columns in the data, whereas here we have 2, 4, 6 columns in the data, two variables. It's easy. It doesn't matter how many time points there are. It could be 100 time points. We still have two variables here, right? It just expands in terms of the time series. So we have C sub t regressed on C sub t minus 1 here. And on the between level, we have random intercepts for these guys. I drew it as two random intercepts, one for U1, one for U2. And here, just to make the similarity with the one-factor model, I put a factor behind them. And you note that I don't have any residuals here. So the essential dimensionality is 1, that one factor, and I left the loadings a bit different. So the latent trait, so to speak, has different influence on the two random intercepts. So two outcomes per time point result in two columns of data, not 2 times t, and across time effects are specified by using lags. So there's no need for repeating variables for at time t minus 1 in the data set. It's handled automatically in this time series modeling. So in the DSEM format, which we've written about extensively, you can see the papers here, time series analysis, the theory. There's also RDSEM, residual DSEM, which is more like two-level analysis, where you don't have YT regressed on YT minus 1, but you have the residual of YT regressed on the residual of YT minus 1. We call that residual DSEM. So several papers here about the theory, and the applications are growing here. A recent one in the psych methods is McNeish and Hamaker, a primer on doing this in Mplus. And we have several workshops recorded here, videos that you can take a look at. All right. Now, to be able to do this with all these random effects that I mentioned, you need to switch to Bayesian analysis. And we did that. We offered Bayesian analysis in our program many years ago, and it becomes more and more important for us to have done so. It's a great platform to move the modeling forward on into more advanced models. So if you use Bayes with non-informative priors, which is our default, we see it as a powerful computing algorithm. Analyses are often less computationally demanding when ML requires high-dimensional numerical integration due to many latent variables. And when I talk about latent variables, I mean factors and random effects of all kinds. In cases where ML are prohibitive, Bayes with non-informative priors can be viewed as a computing algorithm that would give essentially the same results as maximum likelihood if maximum likelihood was feasible. So Bayes with non-informative priors in large samples give the same results, essentially the same results as maximum likelihood. We know that. So it becomes a very useful computing algorithm where it allows new types of models to be analyzed, for instance, multi-level time series models. Now, Bayes, of course, has this extra advantage or possibilities to using informative priors on the parameters, which can then better reflect previous studies information and hypotheses based on previous studies. So we have some papers on, for instance, on factor analysis with informative small variance priors for cross-loading, showing how that can fit so much better, much easier tool to work with than confirmatory factor analysis. It's sort of a step between exploratory factor analysis and confirmatory factor analysis. So random effects in two-level time series modeling is, as I said before, random intercept, random slopes and covariates, such as time. You can have a growth model as part of the time series. Random slope then is the slope growth factor. You can have random variance, it's a random residual variance that becomes quite important. Individuals vary in their variation, and they vary in their autoregression, and they can vary in their amplitude, the variation up and down across time. So if you take a look at that, the last part, here you have variation in over time, showing cycles, 1, 2, 3, 4, 5 cycles here. This is actually for heartbeat during the day. So you have biological cycles, 24-hour cycles, like the circadian rhythm, heart rate, behavioral cycles, weekly drinking pattern, and environmental cycles, monthly temperature fluctuations. We're going to take a look at an example where we look at yearly temperature fluctuations in an electricity data example. And we're going to take a look at behavioral cycles with respect to positive affect, happy thoughts, which tend to have a daily rhythm as well, where people get happier middle of the day, afternoon, and then start getting tired and perhaps less happy. What I'm using for this analysis is this Sine-Cosine approach, which is well known in the literature. So you have, it's a function curve, and that has a slope, beta 1 times an x variable plus beta 2 times another x variable, where the beta is and the x's are related to sinus expressions, and beta 2 and x2 related to cosine expressions. They don't have, the beta 1s and beta 1, beta 2 don't have much substantive meaning, so we translate them into amplitude and phase. Amplitude being how much it goes up and down across time. I mean, how high the fluctuation is from the lowest to the highest. And we don't have to worry about these details. And you can actually, if you want to find how many components there are, it could actually be 2 components. It could be weekly variation plus daily variation. And you can find number of components using so-called spectral analysis. So we offer this both in the 2-level and in the cross-classified setting with random effects. So here is an example that I promised in the abstract. We have the electricity data. It's actually Swedish firms up north in Sweden. And the data come from Schultzberg. And it's firms' electricity consumption measured daily It's also existing in hourly fashion. But daily over 3 years, t equals 10,096. Maybe it's 95 actually, 3 times 365. So it's a long data set, very long. And the intervention is a change in tariff, how they charge for the electricity. And we have 184 intervention group firms and a bunch of control group firms not shown here. And the interesting thing is that we have long pre-intervention data for 1 year. Wouldn't you want to have that? And post-intervention data for 2 years. So we use a Sine-Cosine cross-classified model, and these graphs come from Mplus. So it's actually takes a little while to read what these curves show, but you see the cyclical pattern, of course, with higher amplitude on the left and on the right. So the left part of the figure, the curve after the intervention here is after 1 year, shows the predicted development in the absence of the intervention. So it doesn't change before and after this line, right? It's the intervention group. So this part of the curve to the right of the line is a counterfactual in the sense that that didn't happen to this group. That didn't happen. This happened. This happened. And on the right part of the picture, you see what happened after the intervention to the right of, it's the same group of individuals. Now after the intervention, to the right of the intervention, the amplitude goes down. This part, the backcasting here, as opposed to forecasting, is counterfactual. That didn't happen to these people. So what happened is, you have to piece them together. What happened is you have, this is the treatment group once again, this happened on the left here. So you should piece this together with what's on the right of the line here. To the left of the line here, to the right of the line there. And then you see the drop in the amplitude. And the level also, I think. But it's interesting that you can plot the, sort of plot the counterfactuals in this way. Now, here we're just talking about the intervention group, not the control group. And even if we analyze the control group, this was not a randomized intervention. So what was done here is a non-experimental situation where matching on the propensity score was used. So here on slide 37, you have a propensity score analysis in the setting of intervention modeling and multi-level time series analysis. So no randomization, matching on propensity scores. The propensity scores obtained from pre-intervention random effects. So random effects of the pre-intervention time series are used for matching to evaluate the post-intervention outcomes. So if you look at it from a modeling point of view, you have the time series at the bottom, electricity at time t use, influences electricity use at, oops, these should be reversed, should be t minus 1 here and t here. And you have various random effects, these filled circles, random intercept, random autoregression, random residual variance, random amplitude, we don't show that here. But those random effects become these between level latent variables, continuous latent variables on the between level, on level 2, which is the variation across firms. Whereas at the bottom, we have variation across time. So you have these random effects from the pre-intervention time point influencing an observed between level variable, namely the intervention variable, 0, 1 intervention variable. So it's a latent observed variables, latent random effects influencing the intervention probability. From that, then you can get the estimated probabilities, which are the propensity values, and do the match. So that's what this Mr. Schultzberg did in a paper in 2019. It's actually paper number 1 in his doctoral dissertation in statistics. And it turns out that my nephew, who is now this Mr. Schultzberg, got his PhD in the same stat department at Uppsala University as I, some years later, I should mention. Up above my head here, you see me as a very young 1977 PhD, with the Swedish oak wreath on the head and a diploma in hand and a tuxedo, of course. We got the opportunity to write a paper together in 2018 in the DSEM journal, which gives you suggestions for how many subjects and time points that are needed for multi-level time series analysis, related to how many random effects you can handle. And now this young man has gone on to become employed as a data scientist at Spotify in Stockholm, which is an interesting development to follow from a distance. But we're still collaborating. Now, if you go to intervention modeling in multi-level time series analysis for the case of randomized studies, what would you do? How would you do it? Well, let's say that you have these rich data with a long pre-intervention time series, before the treatment and after the treatment. Well, you have these random effects then that summarize, the random effects is a good summary of the pre-intervention time series. Which level are you at? How strong is your autocorrelation? How high is your amplitude? How high is your variation? And you have the between-level treatment, and it influences the post-intervention random effects. And it also may interact in their influence on those effects, interact, that's the broken arrow here, with the pre-intervention. So that those with especially high levels benefited more, or those with especially high autoregression benefited more from the intervention. It's kind of interesting when you have rich data like that. So you wonder then, well, do these data actually exist? Yeah, they do. Here is one example from JCCP, Journal Consulting Clinical Psychology, Geschwind and others. Momentary positive emotion, a randomized controlled trial. So these are data that I'm working on in a paper with various co-authors who know about the substantive aspect of this. They use experience sampling methods. T equals 60 pre, T equals 60 post. And each period has 10 beeps, random beeps per day within certain time frames. Via digital wristwatch for 6 days, so 10 times 6 is 60. Sample size is a little over 100 individuals. So I applied DSEM, applied DSEM with daily cycles in positive affect, which is a frequently occurring variable type in these studies, modeled by sine-cosine curves with random effects. So bottom here you have you see these cycles, these fluctuations, 1, 2, 3, 4, 5, 6. These are the 6 days. And you see that positive affect tends to go up in the middle of the day, and like that. So superimposed on the observed means here over time, over people at the different time points, I should say, you have the estimated sine-cosine curve. You see that it's reasonably well capturing what goes on. You have a little extra variation here. If you want to, you can also take into account weekdays, which may have a different effect than what can be modeled by the sine-cosine curve. So that is an example of just what we talked about, namely the pre-intervention random effects influencing the post-intervention random effects differently in the treatment and control group, and so the treatment effects interact with pre-intervention features. Preliminary findings, we're still working with these data for intervention effects on the random effects of the post-intervention time series for the momentary positive emotion, they call it here. Positive effect on level, post-intervention level. The treatment has a positive effect on the post-intervention level, and a higher effect on level for persons with higher pre-intervention level. So it's like those who are already happier benefit more from the treatment. And it's also interesting, a positive effect on level for persons with high pre-intervention autocorrelation. This autocorrelation has a substantive meaning of so-called inertia in psychology. And I'm looking forward to hearing from my substantive colleagues why this might happen. But it's an interaction effect between pre-intervention random effects and the treatment. All right, we'll come to the last bullet, and I think we have a couple more minutes. Bayesian analysis continues here, as we did in multi-level time series analysis. We have it also in the last bullet. We're going to take a look at count and nominal and binary logit outcomes for Bayes, which has long been recognized as a hard problem in statistics. This is a quote from an article in JASA, Journal of the American Statistical Association. If you think about this for a second, if you look at binary loaded outcomes first, why it is a hard problem is that binary probit is so much easier than binary loaded, because binary probit in the Markov chain Monte Carlo algorithm, in the iterations, you can work with underlying latent continuous response variables that, when they pass a threshold, gives rise to one or the other observed category. Albert and Chib, I think it was, or Chib and Albert wrote about this problem many years ago, and it's quite easy to do because of this underlying multivariate normal distribution. But it escaped folks, statisticians, how to do that for loaded. With logistic regression, you don't have that underlying multivariate normal or any other continuous latent variable exceeding thresholds or not. It took quite an effort to develop that, and it's based on so-called polygamma variables that are used in the drawing of random numbers within the Markov chain Monte Carlo algorithms of Bayesian estimation. So that's solved then the binary logit situation and also the count situation. You know, when you have these positive integer outcomes. How many times in the last week did you, etc. And also solve the nominal case. So we took that to heart. We discovered it and worked on it. Tiermer is the one who really is the algorithmic guru. And just finished a paper which you find on the website, expanding the Bayesian structural equation model. So we put this all in a totally general structural equation model, richly parameterized for both single level, multi-level, and also for mixture models, to loaded situations, negative binomial, which is the one count outcome type, and nominal variables. So it allows many latent variables in the general modeling framework. And the count modeling uses the negative binomial, which is in the MB2 parameterization using the notation of Hilby's book. But also we can do Poisson modeling, which comes out as a special case. And we put that into the new Mplus version 8.5, which was released last Monday this week. In that paper, in that JASA paper, they consider an autoregressive time series model n equals 1 model for count data. And Tiermer took as an example a multi-level version of that in his writing. And here it is. It's an example with 10 time points, 10 count variables. Now you recognize this up here as a random intercept. And you have the within person variation in terms of latent variables, dynamic regressions going on here. This would lead to 11 dimensions of integration with ML, so it's intractable. Bayes seems to work fine from simulation studies, at least when you have at least 500 observations. So for the statisticians among you, the Y counts have an negative binomial parameterization 2 with mean nu sub I, which is a random intercept with a certain mean and variance, and then a time varying component eta sub it, which has an autoregressive series across time here, which we draw up there. So you have 5 negative binomial parameters as listed here. Alpha, I forgot to mention, that's the so-called dispersion of the negative binomial. That parameter which makes it more general than Poisson in the sense that the mean and the variance don't have to be the same as they are in Poisson. So that's quite a simple model in a sense, because it's univariate, one variable, 10 time points. And it's just a random intercept model, but nevertheless, it becomes intractable for ML. So that's why we needed that to make our package more general. Now, why am I showing you this? Well, because it relates to something many of you are more familiar with, namely cross-leg panel modeling, random intercept cross-leg panel modeling. Hammacher in 2015 presented this paper. And if you just look at the top part of the model here, the Y's, it is a random intercept model, right? It's exactly what I showed you in the previous slide, although the random intercept is pulled from up here down to over there. And what she added was a bottom part, so it's a second variable, which also has a random intercept, and the random intercepts correlate. And then the within person across time variation is a cross-leg panel model now for latent variables within here. So what we're working on in my group here is extensions of her work to count and categorical outcomes. So you can have a count here, continuous here, or a dichotomous here, and a continuous or dichotomous count. So we're trying to figure out how to do that in a way that both makes sense and is numerically, software-wise, practical. And it's harder than you might think in some sense to do that. It's not a straightforward matter. But we have noticed here with our customer questions how many people would like to see a development of this kind. Now, it all comes back, of course, to University of Connecticut. 1995 origins. This model was presented already by a certain David Kenny. This figure 2 bivariate case, trait state error model. Here you have it, the random intercept here, he calls it trait, and the random intercept here. It was already presented here, slightly different parameterizations and modeling opportunities, but the idea is the same as in this model and in this model. So it's interesting how it all hangs together, very down-to-earth modeling efforts, but now with more challenges in terms of variable types and in terms of the number of time points. So we're trying to close the circle in that fashion. And if you're interested in reading more about this, we have a section on the website of the recent papers. You find it on the homepage here on the right, or in the recent papers here. And that's what we've written lately. And if you want a fuller list, you look at Mplus papers there. So we have a couple of different ones. This is nesting and equivalence testing, or models nested. Well, Peter Venter came up with a way to do that that we built on and made practical in the Mplus program. Here are the technical reports I referred to for making the random intercept LTA more practical. Random starting values, multi-stage optimization, and base nested parallelization in the computation. Quite ingenious, using different cores operating in parallel. And here, Bayesian estimation of single multi-level models with latent variable interactions, fairly new paper. And here, more of fit indices in Bayesian modeling, taking some of the frequencies fit indices into the Bayesian setting. Here's a paper on centering latent centering instead of the observed centering, like observed group mean centering. It's often better to do so-called latent variable centering, both with mediators and in other settings, multi-level time series models. And here, a more overview paper comparing models for the analysis of intensive longitudinal data. And here is the latest paper that I just mentioned, the expanding Bayes to loaded count and nominal variables, including nominal factor analysis, which is an intriguing topic. And then here's another paper with Ellen Hamacher. Her paper, she took the lead in fixed versus random effects debate, which is a debate in economics. And I talk about that and how it relates to multi-level modeling in Web Talk 1. And then the forthcoming paper should be available online very shortly for RI-LTA.